In the silent immensity of the cosmos, where gravity sculpts the paths of worlds and the faint light of distant stars whispers through the dark, something has begun to move against the familiar order of things. Tonight, we return to a story that has fascinated scientists, astronomers, and dreamers alike. The ongoing mystery of Three-Eye Atlas, the third confirmed interstellar object ever detected within our solar system. Yet what has happened in recent weeks has taken this mystery to an entirely new level. On the 29th of October, as the object approached its perihelion, the closest point to our Sun, something extraordinary occurred. Observatories across the globe caught their breath. The Atacama Large Millimeter Array, or ALMA, recorded a deviation of 4 arcseconds from the predicted trajectory. 4 arcseconds, an angle so small it would appear meaningless to the untrained eye, yet in the precise language of celestial mechanics it speaks volumes. It tells us that something beyond gravity itself may be pushing Atlas through the void. The concept of non-gravitational acceleration is not new to science. Comets often exhibit such behavior as volatile ices sublimate and jets of gas push them gently, altering their course. But the case of Three-Eye Atlas is different. This is not a small icy wanderer shedding frozen breath into space. This is a massive, dense object, millions of times heavier than the legendary Oumuamua that first alerted us to the existence of visitors from other stars. If Atlas truly is experiencing a non-gravitational push, it should be shedding an immense amount of mass. Billions of tons of material vaporizing into a luminous shroud. Yet, telescopes that monitored its glow found no such debris, no tail of gas, no expanding cloud that could explain such a force. Instead, what they saw was even more perplexing. The object became brighter, more radiant, and shockingly blue, bluer than the sun itself. For seasoned observers, this was not merely curious, it was disturbing. ALMA's data revealed not just a deviation in position, but a suggestion of active propulsion, a term that in astronomy raises uncomfortable possibilities. And the Solar Observatory so soon confirmed a transformation in Atlas's spectral signature, a chromatic shift unseen in any known comet or asteroid. The wavelength analysis indicated emissions consistent with materials unknown to natural bodies. Could this be a trick of observation? An illusion caused by solar scattering? Or is there something else at play? A phenomenon that defies the ordinary laws governing celestial objects. Such questions strike deep at the heart of modern astrophysics. Since the first detection of Oumuamua in the year 2017, the scientific world has wrestled with the notion that our solar system might be visited from time to time by travelers born beyond our star's reach. Oumuamua's odd acceleration and its thin, elongated shape ignited debates that still burn to this day. 2 years later came Borisov, a much more typical comet, icy, bright, and natural. But Atlas is different. It stands between categories, refusing classification, as though deliberately crafted to blur the line between the natural and the artificial. And now we stand on the threshold of revelation, because on the 19th of December, in the year 2025, mere weeks from now, Three-Eye Atlas will make its closest approach to Earth. If it has lost the billions of tons of mass that physics demands, the resulting debris cloud will be unmistakable. Every major observatory on the planet will see it. But if the sky remains clear, if no cloud appears, if the object continues to accelerate without visible cause, then we will have encountered what scientists are already calling the 10th anomaly, a body that moves without the loss of matter. Such an object would challenge everything we understand about thermodynamics, energy conservation, and celestial mechanics. The implications are staggering. For if Atlas is not behaving like a comet and yet not like an asteroid either, then what is it? A fragment of an ancient world, rich in metallic alloys unknown to our system. A probe, perhaps, sent by an intelligence that predated humanity by eons, or simply a natural phenomenon so rare that it forces us to expand our concept of what natural truly means. The tension lies in that uncertainty, the haunting space between the known and the unknowable. Even Professor Avi Loeb of Harvard, one of the most respected voices in the field of astrophysics, has spoken with cautious fascination about Atlas. His calculations suggest that gravitational lensing caused by our sun could reveal further secrets about the object's structure and trajectory. The curvature of light, a subtle bending, measurable to a fraction of an arcsecond, might unveil whether its surface reflects, absorbs, or emits in ways that betray hidden composition. Loeb's prediction of a measurable deviation of 0.27 arcseconds has already set research teams preparing their instruments for December's observation window. And so, as we await the approach of this silent wanderer, the stage is set for what could become one of the defining astronomical events of our century. The evidence is mounting. The data are unsettling. The mystery deepens. What we are about to uncover may redefine the boundaries between physics and wonder, between observation and imagination. The story of Three-Eye Atlas is far from over, and the next chapter promises to test not just our instruments, but the very limits of human understanding. When the first signals from the ALMA observatory reached the data centers on that crisp October evening, scientists were not expecting history to unfold before their eyes. The readings were routine, a standard trajectory confirmation of the interstellar object Three-Eye Atlas as it skimmed through its closest pass to the Sun. But the numbers refused to align. The object's predicted coordinates did not match the observed position, not by kilometers, not even by fractions of a degree, but by precisely 4 arcseconds. That tiny discrepancy, barely enough to separate 2 stars in a telescope's eyepiece, carried the weight of something extraordinary. It meant that Atlas was moving in a way gravity alone could not explain. The initial response among astronomers was cautious. Non-gravitational forces are a known part of cometary physics. As a comet approaches a star, volatile compounds within its nucleus begin to sublimate, producing jets that can alter its trajectory. But when teams from ALMA and the Solar and Heliospheric Observatory began comparing the velocity profile with the mass estimates gathered earlier in the year, the calculations became impossible to reconcile. For an object of Atlas's immense density, the measured deviation implied an outward force equivalent to what would occur if over 5 billion tons of material were expelled in a matter of hours. Yet spectroscopy and photometric data revealed no trace of that ejection. The space around Atlas was pristine. There was no coma, no dust trail, no dispersed ice reflecting sunlight. The object was accelerating, but without losing mass. That alone would have made the event one of the most puzzling in the history of cometary observation. But the story did not end there. As the Solar Observatory so turned its sensitive instruments toward the object, it captured something never before seen. The reflected spectrum from Atlas shifted dramatically toward the blue. Its brightness surged to more than twice the predicted magnitude, making it briefly one of the most luminous objects in the inner solar system. The color index suggested temperatures or reflective properties utterly inconsistent with water, ice, or silicate rock. What could cause a body to grow brighter and bluer as it neared the searing heat of the sun, when every known comet fades or disintegrates under such stress? Research teams across the world began to collaborate in real time. Observatories in Chile, Hawaii, and the Canary Islands synchronized their observations, each confirming the same anomalies. The spectral analysis carried out by the Keck Observatory revealed an unusually high ratio of nickel to iron, a ratio more reminiscent of engineered alloys than of natural asteroid material. While no one could claim definitive proof of artificiality, the data demanded explanation. Nature, after all, leaves patterns. And these patterns did not match any catalogued celestial object. The European Space Agency's solar orbiter captured ultraviolet imagery showing narrow, coherent beams of emission extending sunward, an apparent anti-tail directed toward the very star whose radiation pressure should have blown it away. It was as though Atlas were defying the rules of solar dynamics, turning its reflective face deliberately toward the source of greatest heat. Such behavior had never been documented in any comet. The team from the Max Planck Institute for Solar System Research published a preliminary report suggesting the possibility of a magnetic interaction or plasma confinement effect. Yet the measured magnetic field in the region was far too weak to produce such a phenomenon. Something else, some internal mechanism, seemed to be at work. As the data poured in, attention turned to the series of anomalies already known about Atlas, 9 in total before the October event. Each of them, taken alone, could be explained by chance, measurement error, or coincidence. But together, they formed a pattern so improbable that it defied statistical logic. The retrograde trajectory that mirrored the plane of the solar system with an accuracy of 5 degrees. The unprecedented sunward stream, the mass-to-velocity ratio that placed it beyond the known limits of natural formation, the precisely timed alignment with multiple planets at the moment of solar occultation. Each detail added weight to the growing sense that this object was no ordinary visitor. When Professor Avi Loeb, the astrophysicist from Harvard University known for his work on interstellar anomalies, analyzed the available data, he found something striking. Using models of solar radiation pressure, gravitational focusing, and tidal forces, he demonstrated that no combination of known natural effects could reproduce the observed motion without invoking an internal energy source or propulsion mechanism. His suggestion was measured, not sensational. Science, he emphasized, demands open inquiry when the data do not fit. Yet his conclusion was inescapable. 3I Atlas might represent an entirely new class of interstellar phenomena, or something engineered for purposes beyond our comprehension. The implications rippled through the scientific community. Some teams proposed that Atlas might be composed of ultralight materials with a high reflectivity coefficient, allowing solar radiation to produce measurable thrust. This hypothesis had been raised earlier for Oumuamua, but in Atlas's case the mass was far too large for photon pressure to account for the acceleration. Others speculated about cryovolcanic vents releasing jets of exotic gases. Yet again, the absence of any coma or spectral lines from such gases ruled this out. What remained was the data itself. A motion inconsistent with gravity, a composition inconsistent with comets, and a luminosity that increased where physics dictated it should decline. The more scientists looked, the stranger the picture became. The Hubble Space Telescope's high-resolution imagery revealed a surface with sharply angular facets, unlike the irregular, eroded shapes of typical small bodies. Radar echoes from the Deep Space Network suggested a hard, metallic composition, with reflections varying cyclically, as though the object were rotating with a precise periodicity of 6 hours. This regularity hinted at a structured body, not the chaotic spin of a natural rock, and then there was the matter of its origin. Trajectory reconstruction traced Atlas's approach vector to within 9 degrees of the same celestial coordinates from which the famous WOW radio signal had been detected in 1977. The statistical coincidence, a mere 0.6% probability, rekindled public fascination and a storm of speculation. In July and August of 2025, long before its perihelion passage, instruments had already detected the peculiar sunward jet that defied known physics. Now, after perihelion, with the blue flare and the non-gravitational acceleration added to the list, Atlas stood as a catalogue of impossibilities. Its water content, measured at only 4%, challenged the very definition of what a comet is. Its extreme negative polarization of reflected light, below any previous record, suggested a surface interacting with photons in a way unknown to natural substances. Each anomaly was a door into deeper uncertainty. For planetary scientists, this was both exhilarating and unsettling. If Atlas was natural, it meant the universe could produce materials and behaviors far beyond our current models. If it was not, the implications reached into the philosophical core of science itself, that intelligence capable of interstellar engineering might exist, and that its artifacts could drift through the galaxy, occasionally passing close enough for us to glimpse them. Yet Loeb and others insisted on restraint. Extraordinary claims, they reminded their colleagues, demand extraordinary evidence. The coming December encounter would provide that evidence, one way or another. In preparation, nearly every major observatory on Earth adjusted its schedule. The James Webb Space Telescope allocated time to capture the infrared spectrum, searching for thermal signatures that could reveal hidden propulsion or unusual heat distribution. ALMA continued to refine its measurements, aiming to detect even the faintest trace of ejected gas. The European Southern Observatory's Very Large Telescope planned polarimetric scans to measure light scattering at nanometric precision. Every eye, every sensor, every algorithm was now turned toward this single enigmatic traveler. Meanwhile, computer simulations sought to model its possible compositions. Teams from NASA's Jet Propulsion Laboratory proposed scenarios involving nickel-iron composites interlaced with microporous structures, allowing differential heating to create thrust without mass loss. A theoretical construct never observed, but not entirely impossible. Others imagined superconductive materials interacting with the solar magnetic field. Each model stretched the boundaries of known astrophysics, yet none could perfectly fit all the observed data. The universe, it seemed, was presenting a riddle with pieces from multiple puzzles. And as the weeks passed, a quiet awe began to settle over the community. Observers who had spent decades studying predictable celestial mechanics now found themselves facing an object that moved as if guided by intent. It was not proof of intelligence, but it evoked the same unease one feels when gazing into eyes that look back. The patterns were too clean, the alignments too precise, the timing too coincidental. December loomed like a cosmic appointment. Atlas would approach to within a distance that allowed direct radar mapping and possibly even high-resolution imaging. If the predicted debris cloud appeared, then the mystery would shrink back into the realm of natural physics. A spectacular but explainable cometary event. But if the sky remained empty, if no halo of dust enveloped the object, the 10th anomaly would be confirmed. An acceleration without mass loss. A motion without thrust. A force without cause. For humanity, that would mark a turning point. It would mean that somewhere in the vast, unending dark, there exist principles we do not yet comprehend. Forces or technologies that manipulate gravity, light, and momentum in ways that our equations cannot yet describe. The scientific method thrives on such frontiers. It is there, in the uncomfortable space between knowledge and mystery, that discovery is born. As of now, the data remain open, the interpretations provisional. But one truth has already emerged. 3i Atlas has rewritten the conversation about our place in the cosmos. Whether it proves to be a new category of natural object or evidence of something far older and wiser than ourselves, its passage through our solar system will be remembered as the moment when humanity once again looked into the abyss of the unknown and realized that the universe still holds secrets vast enough to humble even our most confident understanding. Soon, telescopes will gather the light of its closest approach. Algorithms will translate that light into numbers, spectra, probabilities. And somewhere in those numbers, hidden between the digits of uncertainty, may lie the answer to the question that has haunted our species since it first looked at the stars. Are we truly alone? Or are we only just beginning to recognize the signs that we are not? To understand the full magnitude of what 3i Atlas represents, one must look back through the long and patient history of human observation. The generations of astronomers who spent lifetimes charting points of light in the sky, each measurement a fragile step toward understanding the cosmic order. Every era has its defining discovery. Galileo's trembling hand guiding the first telescope toward Jupiter's moons, Edwin Hubble revealing that the universe itself was expanding. And now, in this modern age of radio arrays and infrared telescopes orbiting far beyond Earth's atmosphere, we may be witnessing a moment of equal consequence. The story of Atlas does not belong only to equations and data tables. It belongs to that deeper current of human curiosity that has always reached toward the stars. The name Atlas carries weight not only as a designation, but as a symbol. The Titan condemned to bear the heavens upon his shoulders. In a sense, this interstellar traveler now bears upon itself the weight of our collective wonder and uncertainty. Its discovery marked the third confirmed instance of an object arriving from beyond our star system, following the paths blazed by Oumuamua in 2017 and Borisov in 2019. But unlike those earlier visitors, Atlas is neither fragile nor fleeting. Where Oumuamua was small and elusive, a sliver of rock racing away before we could understand it, and Borisov was a recognizable comet dissolving under solar heat, Atlas endures. It is massive, slow to fade, and disturbingly coherent. As if it were built to last, as if it were meant to be seen. The telescopes that have tracked it since its first detection describe not a random chunk of debris, but a body of deliberate structure. Its radar cross-section changes with rhythmic precision, implying a steady rotation and defined geometry. The distribution of reflected light follows patterns consistent with flat planes and sharp edges, unlike the organic irregularities of natural bodies. Even the thermal emissions, faint yet measurable, reveal zones of contrasting temperatures. Hot surfaces adjacent to cooler ones, suggesting materials with radically different conductivities. It is as though the object were composed of layers, each responding to sunlight in its own way. To the engineers and physicists studying these readings, such complexity is breathtaking. They speak of reflective coatings, of micro-latticed composites that could explain the unusual polarization of light. They model structures that could maintain stability against rotational stresses that would shatter an ordinary comet. In simulation after simulation, the conclusion returns. Whatever Atlas is made of, it is unlike anything forged in the natural furnaces of stars. And yet this realization brings not certainty but humility. For even if we were to determine that its structure is artificial, what then? Who or what could have built such an object, and for what purpose? Was it a probe, a derelict, a fragment of technology adrift for millennia? Or is it a natural construct born of processes that occur in environments we have not yet imagined? The tidal maelstroms around neutron stars, or the collapsing shells of long-dead worlds? The possibilities are as boundless as the sky itself. Among the many who have dedicated their lives to unraveling this enigma stands Professor Avi Loeb, whose calm voice has often bridged the divide between skepticism and open inquiry. His career, spanning decades of astrophysical research, has been defined by the willingness to ask questions others hesitate to pose. From his early work on the first galaxies formed after the Big Bang to his more recent studies of interstellar visitors, Loeb has always sought patterns hidden in the noise. In the case of 3I Atlas, his message remains the same. Do not leap to conclusions, but do not close the door to wonder. His students describe him as relentless, methodical, yet driven by a quiet conviction that discovery requires courage as much as caution. He often recalls the lessons of history. How many times humanity has mistaken its limits for the limits of the universe. When ancient astronomers believed the stars to be fixed upon a crystalline dome, it was curiosity that shattered that illusion. When Newton defined gravity, it was curiosity that later led Einstein to rewrite it. Now, as Atlas bends the laws of celestial motion in ways we cannot yet explain, curiosity once again becomes our most powerful instrument. If there is poetry in science, it lies in moments like this, when observation transcends the coldness of data and becomes a story about ourselves. Because 3i Atlas does not only challenge the boundaries of astrophysics, it forces us to confront what we are as observers in a universe older and stranger than we can imagine. It asks whether intelligence, wherever it arises, inevitably reaches for the stars as we have done. It asks whether distance and time truly separate minds capable of understanding, or whether the language of mathematics and light is universal enough to be shared across the gulf of eternity. As December approaches, observatories prepare for the most intense campaign of observation in history. Dozens of instruments across multiple continents will watch the sky on the night of the 19th. Radar arrays will listen for echoes, telescopes will dissect the spectrum of its glow, and satellites will trace the faint ripples of its gravitational influence. If Atlas possesses even a thin atmosphere of particles, the scattering will reveal it. If it hides a structure beneath its reflective surface, radar imaging may glimpse its outline. And if the non-gravitational acceleration persists, the data will confirm that we are dealing with something beyond known physics. There is a certain silence that falls over scientists before an event of this magnitude. A silence born not of fear, but of reverence. For in those final hours before observation begins, each of them will look up at the same sky and realize that they are witnesses to history. They are part of a civilization capable of peering across interstellar distances, deciphering signals written in light years, and still feeling awe. In laboratories from Tokyo to Pasadena, from Cambridge to Munich, researchers will pause between calculations and remember that every photon they study has traveled through the same darkness that once gave birth to stars. Whatever the outcome, 3i Atlas has already fulfilled its purpose. It has reminded humanity that the universe is not exhausted by our understanding. It has shown that even in an age of advanced instruments and precise models, mystery still thrives. Perhaps the object is a relic of a distant world, a shard of an ancient civilization long gone cold. Perhaps it is a natural marvel, sculpted by cosmic forces we are only beginning to grasp. Or perhaps it is something in between, a phenomenon that blurs the boundary between the organic and the engineered, between life and mechanism. What will we learn when it passes? Maybe nothing definitive, maybe just more questions. But questions are the fuel of progress. Each anomaly is an invitation to look deeper, to refine our tools, to reach farther. The story of Atlas is the story of human persistence, the refusal to accept the boundaries of ignorance. In that sense, the object is not merely a visitor, it is a mirror, reflecting our unending desire to know. When the echoes fade and the light curves settle into data, when the astronomers publish their findings and the world moves on, something will remain. It will live in the quiet certainty that somewhere out there the universe is still alive with wonder, vast, indifferent, and yet filled with mysteries that respond to the gaze of thinking beings. Atlas may drift on into the black, vanishing among the stars from which it came, but its passing will have left an imprint deeper than gravity, written not in orbits, but in minds. In centuries to come, when future generations look back at the early 21st century, they may see in the saga of 3i Atlas a turning point. The moment when humanity realized that the sky above is not merely a backdrop of cold lights, but a living ocean filled with stories still untold. Whether Atlas is a relic, a messenger, or a mystery beyond comprehension,